first session will be about open source in Julia in science, which I believe
as I said earlier, there's a good licensing argument why you should be doing it. You want to use your code after you left OIST. Anyway, okay, welcome to the next day. I'm happy to see that not everybody ran away. And today we're going to talk about first contributing to open source, and then a couple of nice packages for Julia for Science. And then in the afternoon, we're going to talk about everybody's favorite topic, GPUs. GPUs are fun. Yes. Okay, so why would you want to contribute to open source? Any good answers? It's good for humanity. Collaboration is good. Companies are evil. Amen. None of us pays for software, so we all are using open source software, basically. Yes. I couldn't hear that word. For me, it's fun. You learn a lot doing it. You collaborate with smart people, and they will review your code hopefully, before they merge it. And that process will teach you how to write better code. Like, that is basically how I didn't start out as a computer scientist, right? I started out as a scientist and then wrote code and contributed to open source. And over 5 years of doing that, became good, kind of, at writing code. And the other part is it leads to better science. If you ever try to reproduce anything and they hid their code away on some tape recorder at the bottom of the basement with an 490, you know it's impossible. But it's on a tape recorder. Do you have a tape reader? Why shouldn't you maybe contribute to open source? And I think that's the big caveat. It takes a lot of time. It can turn into a typesync, especially when you start maintaining packages for other people. Sometimes code review can be quite contentious. People have strong opinions. People are bad at expressing opinions. They're bad at arguing, and they're bad at arguing via text. Humans are not good at communication. It gets worse if you're doing cross-cultural communication and you're dealing with people who have very different styles of expressing opinions. Some people are very blunt. Other people say nice things to you, and that means no. So, just be aware. It is like science, right? It's like a science review. And in the end, part of what you're doing is, if you're contributing to somebody else's project, you're telling them, here is my great change. I spent so much time doing this. And you're asking them, take my change and maintain it for the rest of the project. So yes, you spent 10 hours doing everything, implementing the code, writing the documentations, writing the tests, but you're basically asking somebody else to maintain your code until the rest of the lifespan of the project. So be aware of that there sometimes can be a hesitation to take on code project. Start small if you want to contribute to a project. Bug fixes are good, documentation fixes are excellent, adding tests is wonderful. All of those things make people's life easier. Adding a pull request that is 3,000 lines of features without any documentation and any tests will most likely be will not merge. I'm sorry, please break up. Sometimes maintainers spend a lot of time just talking to people and like helping them contribute. Other times they are way overworked, and it's what they do between 9 to 10 after working, then spending some time with family and going to sleep. Right? It's all voluntary work. Some people have the benefit of being a part of the job. I consider like my open source contribution as part of my PhD work. My boss is okay with me spending work time on that. Other people's boss require you to do that outside of work. Yeah. Yeah. If if you're going into a field where that is a norm, which is software development or like technology work, employers are often open to negotiation where you say, I want to spend 20% of my time on open source work. Or I want to work on these open source projects that you are maintaining. Like sometimes companies have open source projects and you want to say, I want to be on this team. There is a fantastic guide on how to contribute, and like condensing it down, I think the important thing is always to say, why am I doing this? What is my need? Am I just wanting to learn? That's fine. That's a good need. But most often what I find myself is I have a feature I really need in this package and I wrote the code and now I just want to make sure that other people can also use it. Or while trying to use this package, I found a bug and I got annoyed, I fixed it, and now I want other people to have that fix as well. So that's what my need is. I want to share that work. Or I had a bug, I fixed the bug, here's the solution, please take it. So that helps you in communication because then you can say, well, not here's my code without saying why you're doing this. You're saying this was my problem, this is how I solved it, this is the code that solved it, and people can go in and say, look at it, is it a good solution? Does the solution fit into the project? Does the code fit into the project? Sometimes it makes sense to just talk first about your problem, open an issue, write to the mailing list and say, hey, listen, would you be okay with me spending time working on this? And sometimes people are like, that seems out of scope. That's not something that should be in this package. And then you're like, okay, just create my own package, right? It's open source, free for all. You can always fork somebody else's project, but then you're stuck with maintaining that fork. And then write up a pull request, have tests, have docs, try to match the standard and the style of the repository you're contributing to. Like if somebody sees C code is indented by 3 spaces and you're indenting yours with tabs for 8, it's not going to match. And the polite thing to do is not to change everything to your liking, is to match the style of the project. And sometimes it just takes time. It's like if somebody sends me a pull request to one of my packages now in this week, I won't get to it for the next 2 weeks. Like I have emails piling up and I'm like, nope, I'm not looking at those because I don't have the time because I'm teaching. And so all of these contributions, I will look at them when I have time, but they have to wait. And sometimes you can just share that burden of maintenance with other people and have like 3 or 4 people looking after a package, and then things go kind of smoothly. But there are lots of pull requests open that I have to review yet, and the list somehow does never get shorter. Okay. Yeah, I mean, that's the other thing, right? Issues being opened, pull requests being opened actually means people are using my stuff. That is exciting. It's like getting an email from somebody who is like, thank you for your work. This has saved me so much time, is like the best feeling. It's addicting. It also offsets all the emails that you get or issues which are like, this is broken, fix it. I'm like, works for me. So general structure, how do I contribute to a Julia package? We talked about this a little bit yesterday, but generally you go into your package REPL, you say dev this package name, then you switch to wherever that was checked out, which will be on most systems .julia/dev/package name. Then I would recommend, so this will be using Git because the entire ecosystem is built around Git. So you can create a new branch, call it bug fix or feature, or name it something that is meaningful, because once you have 20 branches and you trying to remember what each of them was for, you're happy that you had a good name. So as an example, if I go into my Julia repository and I look at all my branches, so I prefix them with my initials so that I can remember that they were from me. And so I probably know that these two had something to do with aliases for memory accesses. This was I probably could have deleted them. I don't quite know which ones I already fixed and closed. I know most of what they were for. I don't know what this is for, as an example, but this I know. These I know what they mean. But yeah, it becomes after 5 years, 4 years. This laptop has only seen half of the time, right? So we can get a look on GitHub and see all the stale branches. Anyway, then you can create your change. Whatever you wanted to fix, your documentation, your tests, your source code. Afterwards, run the tests. Nothing is more annoying than getting a red cross from CI the first time around, which is like, you broke everything. And then commit your change. And afterwards, you now have to do a little bit of busy work, where now you have your change locally, you have a commit locally, and now you need to make sure that you can put that up to GitHub, open a pull request, and hopefully get it accepted and merged. So what it normally looks like is that I go to github.com. Oh, what's a fun one? Static arrays. And I click the fork button here. And okay. Do I have? Which one does I have my forks recently? Probably haven't this one. Now ask me where I want to fork it. It's my personal account. It will tell me it will wait a little bit. Actually, this is a good idea. Okay, so now I have it forked. What I can do is I can go to Julia and say dev QArrays, which is the package we just forked. And it probably makes sense to dev. The difference between add and dev, or adding and developing, means developing will give you a local copy of the Git repository that you can change, that you can edit. And the package will be installed in this path that is displayed here. So you are now, it is no longer resolving a version, it is resolving a path. And any change you have there will be picked up. Whereas if you're resolving a version, it doesn't really exist on the hard drive. It does in a specific place, but you're not supposed to change it. And now I can go to source QArrays. Git remote add vshuravi, and then if you don't precisely know the structure by heart, you can also just go here and copy this link and pass that in afterwards. And this will add a remote. And now if I do git fetch vshuravi, oh yes, and this happens if you don't copy and paste it. So let's remove it and start again and fix the typo. Yay. So these are all the things that are happening there. And so now I can say, let's create a branch here. And we can open some source code. And we just say it's a great idea to just remove everything. That I think this package has no purpose anymore. And then I can Yeah, I think the Marco should have gone in there. Yeah, that would have worked. And so and now the next step is everything, right? If you haven't used Git that much, just as a reminder, everything that I currently have done has only happened on my local computer. I've not published anything, I haven't pushed it out yet. And now I can say git push -u, and instead of saying origin, I say my own repository, and then I say we see nothing. And now these days, GitHub is as nice and actually like tells you that you can go to this URL and open up a pull request. And you see the base repository is Julia GPU/QArrays, and the head repository is vsharavi QArrays from the branch we see nothing. And so now I have this this pull request window can basically say a short description of what I did, then the rationale, and then I can look at my changes. And before I hit submit, I normally look at them and be like, oh yeah, that looks all right, or there are things in here that I didn't want to have. And then I hit create pull request, or there's also the second option these days, which says create draft pull request, if you're not quite sure yet, if you don't want somebody to just merge your code. We will not do this. So the CI build is running on the directory I would make the pull request to. So after opening the pull request, you get the Travis CI build. Or you set it up for your own local clone. So I could go to Travis and say, modern technology, the internet got so fast, but everything else got slow. And everything, all the tests are failing. Great. Oh, yeah. Well, I always forget. How do I add a new one? Why is it only showing me this system? Oh. Yeah, I'm. Ah. Okay. And then I can set. Oh yeah, this repository is not set up for Travis because Travis doesn't have GPUs. Yeah. It's complicated. We are using GitLab as a management, and then we have our own GPU machines to run the tests on. Right. And so once I hit this, it would basically open a pull request, and that might then look like one of these. The cross means that the tests are failing, which is probably why this hasn't been merged yet. And I can click on the cross and look at the test results. tests can generally be flaky. That is part of the issue. You can ask the maintainers to rerun it, or you rerun it yourself if it's your own repository. So generally, this is what the workflow looks like. If you have the GitHub command line client, it turns into up fork, up push, and hub pull request, and it becomes easier than having to remember which things to click. That's hard. That's generally a hard problem, so you don't do it. You rely on the CI the maintainers have set up. So basically, right, you can test it yourself, make sure that it's like reasonable. The test script should normally just work, and then CI will make sure that it's tested across Windows, Linux, Mac, whatever they support. Or you only cache very intentionally. Yeah. Okay, questions about this? Yeah, some other companies I think sponsoring most of it, but yeah. Yeah, DigitalOcean is sponsoring it. Yes. And we normally have like a weekend before we sit down and go through all the open issues and mark them Hacktoberfest, and if anybody wants to contribute them. So this is how to contribute to a Julia package. If you want to contribute to Julia self, you have to first do the annoying part, which is building Julia from source. These days, it no longer takes 45 minutes. It takes more like 15. But it is a C++ and C environment, and so you will have to deal with make and make files. But the procedure in general is very similar. We have a CI suite that you can run with just run all tests, or you can run the specific tests, and you can just clone Julia and then run make on the top level directory. You can also modify what make is doing if you have specific needs, but that's rarer, and hopefully you don't have to go there. No, there's an explicit non-goal. Yep, just uses unlimited parallelism. And right, as an example, I did it this morning to update my local copy of Julia. This is 1.3, which is funny since 1.2 hasn't been out yet. From this morning, and it basically also, right, in this version information tells me when was it, from which commit was it built, how long ago was that, and I can go into my, so I have split things out, that's why it's different, and I can go and we can take a look around and see how Julia actually code is actually structured under the hood. So, right. So there's some nonsense here for me that we can ignore, but the important things is base, standard lib, and then source. Those are the directories in which the source code for Julia lives. And then we have test and docs for testing and documentation. And then everything else is to make sure that dependencies work well, etc. So if you take a look at the standard lib as an example, these are the modules, the packages that are coming with Julia, basically batteries included. So we have linear algebra is a package. It used to be inbuilt into base. Base is the distribution, the minimal distribution of Julia, whereas these are all add-ons. Yes, that is the package manager. It's not hosted on in the source code of Julia. It's hosted outside. That's why it looks like this. And right, you can go in there, and each of the standard libraries is structured like a normal Julia package. So we have the docs, we have a source, we have tests for each of these packages. And then I can go into my build directory and say make -c test, and I maybe want to run the socket tests, which is the standard library I'm looking at here. And so it's only running that part of the test suite. And that'll pass. Excellent. And if I go back and I take a look at the base, no, the tests are written all in Julia. But the script that manages all of them is a makefile and not a Julia script. Because at some point in the build process, you don't have Julia yet. And these are all the functions you normally interact with, right? This is actually the entire implementation of the language. Very little of it is written in C. So the things that are written in C are like intrinsics and built-in functions, which are like, I think there are 110 intrinsics because floating point addition and integer addition are separated things. And we can look at any of these, and let's look at, as an example, iterators or range. Let's look at range. Oh, I like irrationals. And so we have an abstract type definition of what it means to be an irrational, which is a subtype of the real, and we have an irrational itself, and this is how pi is implemented. Those are fun. Where's pi? Is pi in here? Irrationals are numbers that have extended precision definitions, and then you can use any precision range to get the most accurate representation of that. Yes. So pi is 3.14159 blah 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 dot dot dot, which means there's more precision there than actually. Then I can say I want the float 64 representation of pi. That's now a float 64 value, whereas I can also get the float 16 value of this. Yeah. Oh, yes. No. I actually, that is an interesting question. I don't know how many digits we have. We have enough for big float. So this is to, what is my current position? 256 bits of precision. I mean, you have laptops in front of you. Where I would actually be curious to see the definition of pi. But okay, anyway, all of the implementations are here, so we can look at them and we can change them. And it's relatively self-bootstrapped. So the fun part to look at is wait. So Julia starts out live as not a module, but a bare module. A bare module doesn't has anything in it. Like normally a module imports space. And a bare module doesn't have any definition except being an empty namespace. And then you can start building a world in it. You can start using things, and these core.intrinsic and core.ir things are coming from a previous compilation step. We first compile core and then we compile base. And core is very special in that regard. And then we're defining what it means to get and set a property of modules and types and tuples, which we go back to the get field intrinsic. And then we start defining all of these other things that are normal in Julia by bootstrapping ourselves up as we go along, which is a very weird process, but you have some interesting things that happen because of that. And it also allows us to write everything in Julia, so you can go in, look at it, change things, and contribute to Julia. Because in contrast to that, the compiler is actually written in C++ and C and a dialect of Lisp. Because Lisp, yeah, Femto Lisp. It's a dialect of Lisp, a very small dialect of Lisp. And all of this is normally things that many users don't need to touch. Because this is things like code generation, garbage collection, threading, mostly implemented here. Okay, any questions up to this point? Who defined the that's probably Jeff Besançon. He's one of the original 5.4 developers of Julia. We can actually, yes. Oh God, do we have to? This isn't. Yes, I think that should work. So, started all in 2009. Oh yeah, we used to have lists that were denotated by curly braces. Very early on, I think. But yeah. Okay. So One recommendation, if you're like interested in what other people are doing, is just look at the talk list for this year's JuliaCon. There are many fun talks happening. A lot of them are about science. It's not just about I built this tool for Julia or I made Julia 10% faster. It's not. It's more about showcasing what the community is up to. And if you are doing anything with differential equations, I'm not going to talk about it because I don't do anything with differential equations, but there's a huge ecosystem around that. It's being live streamed. JuliaCon is being live streamed. I picked out two projects that I have more in-depth knowledge about. And one of them is Celeste.gl, which was a 2018 and 2017 project. And the goal was to take a catalog of raw astronomy data and use Bayesian variational inference to categorize each possible light source and to determine whether or not it was a star, it was a galaxy, and create a full catalog of the known universe. There was a talk at JuliaCon in 2018 about this, and there are two papers, one about the computational structure and the other one of the science bits of it. And my slides are broken here. They did, this was a big HPC project in the end. So they had 178 terabytes of image data to process to estimate 188 million stars and galaxies. And they only had like 50 minutes to do it. Because this was meant to show that if the astronomy community starts producing more and more data, you can actually do processing of data in a day. So the next stage of a telescope going online are producing like magnitudes more data. How are we going to process them if we are going to need to run the world's fastest supercomputer at the time 24/7 to process them? And so it was, the goal was to be fast, and it's actually hard to get this much data onto a computer that quickly. It was written with Knight's Landing, Intel's Knight Landing architecture, which, you know, just forget about it. It doesn't exist anymore. We still have it at OIST because, anyway, there's a lot to say about Knight's Landing and it being a disappointing product. We did achieve a 1.45 petaflops, which was at the time the first petaflop application that was not written in C, C++, or Fortran. It was 95% Julia code. And it also demonstrated for the first time that you can actually do Bayesian inference on such a big data set efficiently. The second project, which is ongoing, is the Climber project, which I'm part of the collaboration for that. And it's a climate modeling project for between Caltech, MIT, the Naval Postgraduate School. And their goal is to enable to give a much lower estimate, a much tighter estimate for CO2 cycle and the effect on the climate that it has. So right now we have a lot of different models and they have a lot of different error bars and uncertainties in them. And so to bring those uncertainties down, they decided to go back to the drawing board and implement a climate model from scratch instead of working off 20-year-old code bases. It's implemented wholly in Julia, and it's using GPUs, and they are trying to do something very ambitious in a very short amount of time. And they decided, instead of trying to mangle either Fortran and convincing scientists to use Fortran, or having to manage something that is C++ plus Python, they wanted one language to be able to do performance engineering through the system, and have their users use something high level as well. It's a very nice project, very big, a lot of work. It's all, yes, it's all on GitHub. Right now, you can go and download a climate model and start simulating climate. And the tests are passing, so that's good. And we have dogs. But yeah, it's 99.1% Julia code. Documentation MD, I think, and stuff like that. And there are a couple of other projects as part of this. One of them is, so if you do, does anybody do fluid dynamics here? Okay, so this is a discontinuous clerking method. And then they also have an implementation for non-hydrostatic oceans that is fixed volume. Words disappear. Anyway, yeah, that's a lot of fun. And also one of the reasons why I actually started using Julia is because if we can't do research on topics like climate science quickly enough, if the technology we have is slowing us down, I'm not a good climate scientist. I don't have the training for it, but I can help scientists do research quicker and more efficiently. Two very fun tools. One of them I showed yesterday a little bit. It's Unitful, and the other one is Measurements, which allows you to do things like this. Given something in meters and something else in meters, give it some uncertainty of ±1 and ±2. What is the resulting uncertainty or measurement uncertainty? And they just work with each other. It's very nice. One of the things we are trying to push for is being able to compose libraries together. And you can only do other things like calculate Ohm's law. And right, basically, the only thing you need to do is you do not need to you're not allowed to strongly type your methods. All of this works by providing types that overload behavior, that change, that use multiple dispatch to select the right implementation. And if you strongly type and say, I'm only accepting float 64 here, then you can't use any of these tools. It also integrates nicely with plotting. I can use measurements.gl and just say, this is my uncertainty at this point, or I'm pulling that out of my data set, and then it throws error bars instead to measure that. I can change that and be like times and now I have some noise here that is happening. Some of my favorite tools to work with data or make code efficient is static arrays and structive arrays. Static arrays is basically fixed size arrays. I have an array of size 3, arrays of size 20, and I don't add elements to it. And so the compiler can heavily optimize those. And if you're doing anything with images, I would recommend images.gl. It's a fun package. Okay, so what I wanted to do now is to take a step back and say, what kinds of programming language research is currently happening or being developed with examples from Julia that actually impact science. And so one of them is probabilistic programming. Probabilistic programming is basically, I'm not an expert, but my understanding is that you take a stochastic variable and you do your operations on that stochastic variable. And then you can use Bayesian methods to update from some data your posterior beliefs. So let's look at an example using Steno, which is a package for Gaussian processes. Right, we just use it, we import it. We define our model here, which the GP stands for Gaussian process. And this is the prior distribution. And so I have two stochastic variables, F1 and F2, and I'm doing some operation on them. In this case, I'm just having a third dependent variable on it. Now I can randomly sample some data, right? We don't have any, we are not modeling anything real here. We're just having a toy model. So let's sample some data, but we're only observing data for X1 and X3. We use the output here to produce some observations, and then we calculate the posterior processes under given the data and the model. So that if you're familiar with Bayesian, that should feel familiar. Yeah, didn't want to add a zero here. And then we calculate the posterior marginal distributions. We sample for the posterior from all of them. And then we end up with a graph like this. And that was my main motivation. This graph looks cool. But what I want to point your attention to, we have F1 in red and F3 in blue. And basically, we only sampled and updated data. So we only had data for F1 and F3. We had no data for F2. But we had a model that said this is our assumption of how these processes interact with each other. And so all of these explicit data points here are what we had. And then we're using Gaussian processes, and we're building up a model of our data and the unobserved hidden process, which is the green arrow bars. And all of these blue ones are basically like these uncertainty cones. Are how well do we know in this area that this model is actually accurate. So Y is X is input and Y is response. It has no meaning. It's just sampling data. So you can look at the code. I uploaded it this morning. And this kind of like describing models of systems and then exploring, like using probabilistic programming to figure out where are actually, like, if you just had fitted your curves, you wouldn't have any knowledge about the uncertainties here. That is an important information to have as a scientist. How good does my data actually fit my model in all of the region? Am I missing data somewhere? The ability to explain hidden variables. I think that is very cool. And the other two packages I mentioned go behind Gaussian processes. Steno does only Gaussian processes. No, this was before these kinds of packages became prominent. And I mean, there were already in other languages Bayesian packages for Bayesian programming, probabilistic programming with Bayesian methods, but Celeste did it all by hand, basically. The other thing is differentiable programming, which is this funny term which basically means machine learning, but for science. And the idea is that a lot of processes that we are doing in science, we either need adjoints for them. Like if I want to figure out the sensitivities of a model, I need one way of doing that is by getting the derivative of the model and then using that to determine my sensitivities. And machine learning has done a lot of research in the last couple of years of becoming good at getting derivatives of programs. And so the difference between just saying automatic differentiation really is we want to differentiate arbitrary programs and not just specific models. And so you can, if you have reinforcement learning as an example, what you normally do is you have your controller model, which is like a normal neural network or whatever you want to do. And you use automatic differentiation to get the gradient with respect to your parameters. What you can do if you have a programming language that supports differential programming is, and in the reinforcement learning, you then have some kind of evaluation that gives you an error signal. And that it might be a physics simulation. Like if you're trying to learn how to balance a pendulum, you have some physics simulation there. And that error signal is then propagated. The step to differential programming is to say, well, we can also propagate, we can also create a gradient for our model itself and use that to jointly optimize the control and the simulation. The simulation doesn't change, but we have the knowledge. The neural network doesn't necessarily need to rediscover the physics. And so it can be more efficient than reinforcement learning. If flux.ml, I should have put the links in. .ai. They had a couple of blogs on this topic to explain what it does. And if you're interested in, like, this is learning how to shoot a trebuchet and using the model of the trebuchet as part of your algorithm instead of just having it to be your signal for learning your error. You can look at that. Also, if you're interested in auto-differentiation, Roger Liu wrote a blog post recently where he was like, okay, let's re-implement reverse AD in a day. And that's fun. And that's what we're doing next. We're going to not do it in a day because we're not doing reverse mode. We are going to take 10 minutes and implement forward mode AD. It's probably going to take at least like half an hour. These lecture slides are from my advisor, Alan Edelman. And the idea is we are going to look at propagating the sensitivities of a derivative through a program and how we can do that very elegantly and very quickly in Julian. We're going to start and define a function that we want to take the derivative of. And because we want to be funky and show that it actually works with arbitrary control flow, and we're not pulling any tricks here, we are going to use the Babylonian method to calculate the square root of x. And so that's an iterative method where you do an iteration. In this case, we're just going to take 10 and come up with an approximation for the square root. And so we can check and say, okay, what if we take any value? In this case, we take pi and take the square root of that and compare it to the Julia version. And I mean, we're reasonably accurate within 10 iterations. And then we can change any value and say, what, 5, and get the same answer, just verifying that this implementation actually works. And well, actually, that was also something that we found suspicious. And this is how many iterations you take and how accurate you are. So, I mean, this is only for 5 iterations because after 5, you can't differentiate the plots anymore. So the dark line down here is actually square root. And the blue line is one iteration. It's a pretty good method. I think you can do better. And also, if I'm looking at this, I would wonder what happens if I get to large numbers. So let's go to yeah, no longer a good method. So what would happen if we say n equals 50? Right. But now we would need to actually do adaptive and figure out if the epsilon between each iteration is actually changing or not. Are we still making progress? So this is fixed iteration counts. Anyway, we could make this more complicated, but who wants that? Except, okay, so we're going to define a struct, which is just a dual number, which is going to have the real value and the derivative at a point. So we're not doing anything, we're not doing finite differencing here. Right, that's another way we could do this. We could calculate it for x, and then take an epsilon step and calculate for x plus epsilon, and use that to use finite differencing to get the derivative. We are actually doing it at a point. And so we're finding this D, which is going to contain that information, and we're going to take the base methods plus division for now, and then convert and promote to implement the sum rule, which is just addition, and the quotient rule, which says takes the primary value, divide the primary values, right? This is the calculation for the primary values, for the real values, and then takes the quotient rule here, where we take the primary value of one, the derivative of the other, multiply it, subtract it, and divide it by j over 2. Then we want to make sure that we can actually like convert reals to our duals, and we say, okay, every time we just get a real, which is any number, we convert it to d with and set the derivative to be 0. And we also, Julia has a whole promotion mechanism where we want to say, okay, if we see an integer and a float, what should happen? And the promote rule says, if you see an integer and a float, go to the float. What we're saying here is, if you see a dual and anything else, go to the dual. And then, with nothing else done, we can take any input and use the dual as the input to our function. And remember, I haven't changed the function at all. We only have methods of Babylonian. Is our one method up there. We don't have done anything else here. And we get a derivative. So that seems suspiciously simple. Anybody suspicious? So what we can also do is we can just calculate the derivative symbolically. Yeah. I can't magic you? That's sad. So that's the only two things that I'm using in the Babylonian algorithm. Is I'm dividing and I'm adding. Yeah. And yes, you can. So right, that's basically the idea is we're just propagating the value through, and at every time we're doing the normal operation, and we're using that normal value to just do all the control flow operations, and then we are keeping track of what the derivative is. Yes. And so if I would have done this symbolically, since we're having an iterative algorithm, so this is, we can just call into symbolic Python for this because we don't have a good symbolics package yet. And we are doing k iterations here only up to 5. And every time we do an iteration, right, this is the first iteration, second, third, fourth, 5. These expressions get more and more complicated. And this is the issue with symbolic differentiation, right? Since we're having non-standard programs, right? We're doing something iteratively. That's not something you normally do in math. Symbolic just goes like, yeah, I'm expanding and then expanding, and we are more and more accurately approximating the derivative. All right, this is the function approximation, and these are the approximation of the derivatives. They get big. Of the Babylonian, we just. And what we could have done is we could have rewritten our code to actually do this in line, right? We get t, which is our normal value, and then we have t prime, which is the derivative value. And we expand all of this, all of the things that gave it as a rule, and we just write it in line. That would have been a way of doing this, and in some applications that I've seen for old school HPC, that's what they would be doing. But we are getting the same answer that we were expecting. But I can apply it to any method. What's happening? Oh, I messed this up earlier today, didn't I? Never change code. Right. What is something is weird? Ah. The word didn't explode. Okay. Yes. And see, we get the same answer, and the algorithm is actually doing the same thing. Right? We're using an abstraction to add these features transparently to our program. And we can. So this is the derivative. And this is only calculating the derivative, and this is only calculating the derivative as well. And this is the symbolic answer. And we can just add the other two methods that we need, basically, right? We need the product rule and we need the subtraction. And then we have everything. And we also added some nicer printing to it, so that the epsilon notation is denotating the derivative. And due to Julia's design and the use of general methods, things like taking the exponent also just works. and complicated exponents work and everything. That is basically, in Julia, it is very easy with like 4 or 5 methods to implement a new number type. And that new number type, if you looked earlier, we were saying D is a subtype of the reals. Where is it? Where's my D definition? Here. It's a subtype of a number. And so basically by saying this is a number, this will behave like a number. If we implement the right functions to make it an actual ring, then all of the other functionality works. I can even put this in a matrix and then do a matrix multiply over it. Yeah. Right, if I have plus, minus, and times, and sometimes people expect other things from numbers. Yeah. Right. If I take sine and cosine, it throws an error and says method not defined. And then I would need to go and say, okay, what is the derivative for that? Well, that will just print line. No, I defined show. Fallbacks to the same, but it would have just printed D anyway. I can define what it means to take to calculate sine on my dual number. Right. So right, if I had a generic sine implementation, right, similar to we took a generic square root implementation. If you had the same thing, some iterative method to calculate sine or some definition for sine, that could work. It's most often more efficient to have these mathematical primitives actually just be defined. And so we have a whole package for this, which is called chain rules.gl. Where you have a whole set of these. Yeah. Wait, this is fine. Okay. Well, the rule for taking the derivative of logarithm is this operation. And all of this, so that you don't have to do it yourself. You can just use diff rules to like get all of these definitions. If you wanted to create a new implementation of forward mode ID. Well, of course, there is actually an implementation of this. Right? We don't need to do this all the time. It's a little bit smarter. It does more things. As an example, it does square root itself. And now we can also do sine because we already have those definitions in place. Right. So if I had g of x equals sine of x plus cosine of x. And here that's the important bit what I'm harking back about, which is this needs to be a generic type, or it at least needs to say like subtype of number. And I can What do you mean with derivative functions? Yeah. No, so we don't have implicit partial evaluation. Jeremy was asking about that earlier. The way of doing it would be to say, Yeah, it would be like, let's define age. Yeah, you can plot that, do that, do whatever you want with it. You can create a lambda, create a new function, whatever you want to do. In this, it's just a variable. It's just a name. I could have also called it A or B or C. It's just anything. Yeah, right. It's just the name of a parameter. So basically, this is just a function definition. The short form. Right. And for those of you who actually do auto differentiation, of course, there's also a reverse mode package, and there's 2 research projects that are trying more efficient variants of those tools called Cygot and Nabla, which I mentioned in the original slides, that are trying to do faster methods, more easily optimizable. These are like the 4 alternatives I would recommend to do this kind of stuff. And I think the rest of the lecture, what I would like you to do is to either take probabilistic programming and try to mess around with it, or to take an NAD tool and mess around with that, and see if you can apply it to one of the problems you're having. Take one of these tools, either one of these differentiable programming tools, or one of these probabilistic programming tools, and mess around with them and see if they can be useful for your work. I can't. But Wikipedia has a good article about it.